We are Team 11, Hoverbike Airfoil. I'm going to walk you through our project as it has progressed over the past 2 semesters. The challenge we were presented for a senior design project was to create a high efficiency airfoil that would operate primarily in ground effect and at low speeds relative to aircraft. This airfoil effectively replaces the wheels of a conventional three-wheeled vehicle. The airfoil will be accompanied by a nozzle in which compressed air is blown through in order to generate a cushion of air for the vehicle to ride on. The airfoil also had to create lift while there was no forward motion of the vehicle. However, any forward motion of the airfoil would also add to the overall lift. Our sponsor approached us with the image in the top left. Our group discussed several design concepts and settled on a modified NACA 8020 airfoil with internally routed ductwork. This ductwork would channel the compressed air towards the underside of the airfoil to give it the cushion of air to ride on. We made some assumptions about the rider and vehicle in order to establish a baseline and generate our design metrics. Based on the combined mass of the rider and vehicle, we calculated the needed lift per airfoil to be 890 newtons. This would need to be accomplished through multiple flow regimes, both through internal mass flow and forward velocities. In order to prove our design works, we decided to perform a large-scale CFD simulation campaign. This was to try and determine what flow conditions are required to create sufficient lift force for hover and for flight. 11 different heights, 6 different nozzle flow velocities, and 5 different forward velocities were tested, and results are shown in these plots. The most obvious concern appears in the middle figure on the slide, which shows lift as a function of height in millimeters. For heights below about 30 millimeters, the simulations show great lift forces, more than sufficient to create hover. But as we increase in height out of ground effect, the lift decreases below the required 890 newtons and even goes negative. The plot on the right picks one single flow condition of 42.19 meters per second forward velocity and 400 millimeters of height and shows how increasing the mass flow through the nozzle increases lift. The plot on the left shows how increased forward velocity increases lift with no mass flow through the nozzle. In order to prove our simulation results to be accurate, we decided to test a 1/7 scale model in the wind tunnel on campus. Pitot tubes and a force sensor were used to obtain the data shown in this table. We tested 3 different speeds at 6 different angles of attack to try and determine if there was a Reynolds number dependence as well as a dependence on angle of attack. Once data was recorded, the different tests were replicated in SOLIDWORKS and CFD simulations were performed. As shown in the table, the difference between actual and simulation results were quite low, which leads to the conclusion that the simulation results are not only accurate but slightly conservative. Here is an image of the wind tunnel testing. Due to testing constraints, the airfoil had to be mounted upside down. After performing some analysis on the first simulations, and more specifically where the airfoil was creating negative lift, it was determined that we had air coming out of the nozzle where we were decreasing pressure beneath the foil because of fast moving air beneath the airfoil. One way to combat this is to add a flap at the rear of the airfoil. The goal of this was to redirect the air coming out of the nozzle downwards, thus slowing down the air and using the change in momentum to create additional lift. 2 plots shown represent percent increase of lift between the original results and the results obtained with the flap. When we were outside the ground effect on the left, the most increase occurred at the higher flow velocities and the higher mass flow rates. Within ground effect, the results were more consistent, but we had a spike at 2 kilograms per second and no forward velocity. This data conclusively shows that the flap would help dramatically. Based on all CFD simulations, we have identified some minimum flow requirements to generate 890 newtons of lift. Our simulations show that above 50 millimeters, The airfoil is out of ground effect and experiences dramatic losses in lift. The reworked flap design can operate outside of ground effect, however. For static hover testing, two quarter scale models were 3D printed. Um, the first version was comprised of two 70 millimeter electric ducted fans mounted to a manifold that channeled the air through internal ductwork. This design was calculated to produce 2.4 kilograms per second of mass flux through the nozzle. The second apparatus was comprised of two 50 millimeter diameter brushless motors paired with the 380 millimeter diameter counter-rotating propellers and a custom drum that channeled air down through the airfoil. This design is calculated to produce a total of 5.6 kilograms of mass flux through the exit nozzle. The third design on the right shown was to be completed once the single airfoil hover test was successful. Here are a few videos of static hover testing. The results from the wind tunnel testing of the 7th scale model showed that our CFD simulations were on the conservative side. This leads to the conclusion that the airfoil design is adequate in producing the desired lift for the projected combined weight of the rider and vehicle during forward flow regimes. All attempts of static hover test have resulted in inconclusive or failed results, leading to the conclusion that the current setup may be inadequate to produce the static lift required to bring the vehicle and rider to a static hover state. Moving forward, we plan to continue the final planned modifications of the airfoil nozzle and subsequent hover test to present to our sponsor.